मैसेज आ गया आपके पास रिकॉर्डिंग स्टार्ट होने का? यस, नाउ इट हैज स्टार्टेड. Okay. Good evening, all the participants. Today we are having the session 2 of this faculty development program sponsored by ATAL on innovation and challenges of energy storage technologies. And today we have with us Dr. P. Chitti Babu. He is with IIITDM, Indian Institute of Information Technology for Information Technology Design and Manufacturing at Kancheepuram. And he will be talking about the role of energy storage and grid synchronization of solar photovoltaic system using pre-filter based PLLs. I would request Dr. Shailendra to introduce our expert speaker to the audience, please.
Thank you, sir. Thank you for the opportunity. And I would like to introduce our eminent speaker, Dr. B. Chitti Babu. He received a PhD degree in electrical engineering from National Institute of Technology, Rourkela, India in 2012. He was an assistant professor in the Department of Electrical Engineering, National Institute of Technology, Rourkela, India from 2007 to 2013. He had postdoctoral research appointments with the Wrocław University of Science and Technology, Poland during 2013 to 2014 and with the VSP Technology University of Austria Republic during 2014-15. Both of these appointments were sponsored by European Commission, UK. He was assistant professor in Faculty of Engineering, University of Nottingham, UK, Malaysia campus from September 2016 to June 2018. Since June 2018, he has been an assistant professor senior grade in Indian Institute of Information Technology Design and Manufacturing, Kancheepuram, India. He was a visiting researcher at the Politecnico di Milano, Italy during 2015 and visiting scientist at Algiers Technical University, Turkey during 2019. He was a recipient of Young Systems Scientist Award 2019 sponsored by System Society of India, and also he received IEEE mass-based research paper from IEEE Madras section India during February 2021. Dr. B. Chitti Babu serves as an editorial board member, associate editor of peer-reviewed impact factor journals, including IIT Renewable Power Generation, IIT Energy System Integration, Control Engineering Practice, Elsewhere, Energy Sources, Part A, Taylor and Francis, and Electrical Engineering Springer, etc. And also he serves as a regional editor of International Journal of Ambient Energy, Taylor and Francis. He has published over 60 papers in SCI Journal, including IEEE Transactions and IET. His current research interests include power electronics applications in smart distribution grids containing renewable energy sources, design of low power photovoltaic system, including MPPT algorithm, control and grid integration of renewable energy systems. He is a senior member of IEEE, IEEE Power and Energy Society, IEEE Industrial Application Society, IEEE Instrumentation and Measurement Society. Okay, so with this, I would like to invite B. Chitti Babu sir for enlightening us with your session. And I would thank to sir to accept our invitation, and he has agreed to deliver this particular talk. Thank you very much, sir. Please.
Thank you, sir. Am I audible, first of all?
Yes, yes, it is very much.
My screen is visible?
Yes. So, sir, it is not in full screen. Can you?
Okay. I
go to the slide slow mode?
Yeah. Is it visible now?
Yes. Now it is okay. Perfect.
Okay. Just a minute. Let me make it in tablet mode so that. Yeah, is it visible, Dr. Shailendra Kumar?
Yes,
Yeah.
yes.
Okay, so very good evening to all of you and respected my colleagues, Professor Shailendra Kumar and Professor Singh. And really, it's my pleasure to be a part of this wonderful FDP in online mode. I think it is ATAL sponsored, right?
Yes.
Okay. So thank you. It's the title itself is a very impressive title, that the role of the developments in energy storage technologies. So hope the participants are enjoying the session since yesterday. Yeah, really thank you, Dr. Shailendra and organizers, and for inviting me to deliver an invited lecture for this prestigious FTP. And thank you again. And I'm going to deliver a talk on a grid synchronization of solar PV system using pre-filter based base locked loop. And prior to that, let me give certain essence of the energy storage. And all of us know that the energy can neither be created nor be generated, but we can convert one form of energy into another form of energy, right? So with that, while converting one form of energy into another form of energy for the mankind, always we invariably convert one form of energy into mechanical or electrical energy, and further we are converting into useful form of energy. Right. So the energy as what we processes, basically we processes the electrical energy, because electrical energy it holds top rank among all energies, because it has a versatility in that sense. So you can efficiently transfer the electrical energy, we can efficiently utilize the electrical energy, and there would be a possibility of energy saving potential as well. Okay, so all of us know that much of world economy is based on efficient use of energy, right? So now with this current situation, as we might be knowing, we faced all the difficulties for past couple of years about this pandemic. That in addition to that, we also faced certain climate change and the global warming and the CO2 emissions that the government of India and I mean including the world, they promote the renewable energy sources for energy harvesting to meet the future energy demand, and also to mitigate CO2, I mean carbon dioxide emissions, and also to mitigate global warming as well. But still, while we generate electrical energy, most widely we use as renewable energy sources. And as you might be knowing that the usage of generating electricity with the help of renewable energy sources are growing exponentially in the couple of decades. And maybe in after a couple of decades, we meet the complete total installed capacity by renewable energy. And as of now, you might be knowing in India, about 37% of the total installed capacity was solely met by renewable energy sources, particularly from the solar photovoltaic and wind energy conversion system. Right. So one of the difficulties encountered while harvesting electrical energy from these renewable energy sources is that they are basically intermittent in nature. Whenever the source is available, then we should harvest electrical energy. So when the source is not available, we cannot harvest electrical energy. Yes, Dr. Shailendra Kumar, am I audible?
Yes, sir. Please go ahead.
Because power has gone in my office, but I felt I think internet is available. Okay.
Oh.
Are you able to follow me? My voice is quite audible, and moreover,
yeah. It is proper. It is proper, and slide is also proper. No issue.
Okay.
Please.
So while the solar, photovoltaic, or wind energy, whenever the sources are available, we are able to harvest. When the source is not available, we cannot harvest electrical energy. But in order to have reliable sources of energy utilization, we promote energy storage, because when the abundant of energy is available, then we can store the energy with the help of energy storage devices. Then when the source is not available, still the energy storage can fed back the energy to the utility, so that we can maintain the continuity of the service in addition to the overall energy or overall meeting the energy demand, right? So the energy storage is very important in electrical system, as it allows for load leveling, and also for peak shaving and frequency regulations, and damping energy oscillations, and improving power quality and reliability. Right. So overall, in the modern power system, or in the smart grid environment, the energy storage is playing a very major role as you cannot imagine a modern power system without energy storage. So invariably we use a different kind of energy sources in the modern utility so that it serves as a candidate for improving overall system performance when the grid is under normal or abnormal grid conditions. So that was one of the motto that the number of courses have been floated by different universities across India, as it has been funded by either SERB or through Accelerate Vignan or maybe through ATAL by ACTE. And that was the motto. But as I haven't done extensive research or something on this energy storage, instead I have done quite significant research on the grid integration of solar photovoltaic system. And we have proposed a number of control algorithm, and also we have proposed a number of phase locked loop for the grid synchronization of solar PV system here in IIITDM Kancheepuram. I could develop a 1 kilowatts grid connected solar PV laboratory here in IIITDM, and under my supervision, 4 research scholars are actively working in this particular area. So what our team have done the work here in IIITDM Kancheepuram that I wanted to explore. So of course, this is one of the very emerging area that even in any modern electrical energy systems, as while integrating renewable energy sources with the utility grid, of course, we need to meet certain requirements, right? So that requirements are going to be met, that has been imposed by a transmission system operator. That requirements are called the grid code requirements. So one of the important grid code requirements while integrating renewable energy with the utility grid is the synchronization. So how perfectly you are able to synchronize the
Sir,
grid.
Chitti Babu sir, you are still
Yes,
in
please.
first slide?
Yes, I haven't changed. Yes, I haven't changed.
Okay, that's
Yeah,
fine.
yeah. No,
I was thinking
yeah.
like slide is not changing.
No.
Okay.
No, I haven't changed.
Yeah, now
them.
it is changing. Yeah,
Yeah,
please.
that is what. So one of the important requirements in integrating solar PV system with the utility grid is the synchronization. So how far you are able to integrate or synchronize the utility grid with the inverter? Because invariably we use this power electronics converter as an asynchronous interface between the solar PV and the utility grid. We are able to successfully integrate the solar PV system with the utility grid. So for successful integration of solar PV system, as we have to meet the grid code requirements that include grid synchronization. So we have taken an attempt, we could be able to develop certain pre-filter based phase lock loop for perfect grid synchronization under different grid abnormalities. Because integrating a solar PV or the inverter with the utility grid during grid abnormality is a difficult task, it's a challenging task. So we would take an attempt to solve such grid abnormalities. We proposed a kind of pre-filter based phase lock loop that I am going to present for next 2 hours. So let me talk about the RPG, that is called renewable energy integration with utility grid. What are all the possible problems associated with renewable power generation integration? Basically, as I mentioned, that renewable energy sources are very intermittent in nature, and the characteristics basically very random in nature. Due to this intermittent or the random in nature characteristics of either solar photovoltaic or wind energy conversion system, it is difficult to integrate with utility grid, as the grid, it needs the power that is going to be injected into the utility grid at a constant voltage and constant profile, constant frequency. But that may not be the case, as the sources are no more stagnant and the sources are intermittent and very dynamic in nature. Due to that, very difficult to integrate. And the second important point is that the generation unit, it never be aligned with the load pattern. Because as the load, it needs a constant voltage and constant frequency, most of the AC load it needs. But as we receive power from the solar photovoltaic is a DC power, and invariably we uses a power electronics converter between the solar PV and the load, so that whatever be the load requirement, that cannot be met by any kind of renewable energy sources, right? Because for example, the wind energy conversion system, it produces always a variable voltage, variable frequency AC power, whereas the grid, it needs a constant voltage and constant frequency AC power. Right. So generation unit, it never be aligned with the load pattern, and there would be a possibility of forecast uncertainty. So while forecasting the renewable energy for identifying the site of the potential especially either wind energy or solar photovoltaic, it is very difficult to forecast. That is one of the key disadvantages of renewable energy sources, particularly solar photovoltaic or wind energy. And one of the important performance issues, the operational performance issues in the renewable energy is that low system energy. Basically, these all renewable energy sources are, particularly solar photovoltaic, is a fragile energy source, as they doesn't there would be an internal disturbances or external disturbance occurs in the utility grid, right? So this was the one of the important issue when integrating renewable energy with the utility grid. When the grid is under abnormal condition, as the grid, it needs the support of a damper to damp out any oscillations or the disturbances to enhance the system stability. But the solar photovoltaic doesn't provide any inertia, so it is difficult to improve the overall stability of the utility grid. And there would be a voltage consistent during islanding. This may be the problem associated with either wind farm or maybe the solar park. So these are the possible problems while integrating solar photovoltaic or wind energy conversions with the utility grid. So for successful integration of such energy sources, usually the transmission system operators or the distribution system operators, they call either TSO or DSO, they impose certain requirements on the power producer. By satisfying such requirements, we are able to integrate renewable energy with the utility grid. That requirements are called grid code requirements, as I said earlier. So these grid code requirements are very important. I mean, almost all the country, they have their own grid code requirements for wind energy as well as solar photovoltaic system. Even in India, we have a grid code requirements of wind turbine. Also, we have a grid code requirements of solar photovoltaic as well. That requirements include controllable active and reactive power. As the grid, it needs a controllable or regulated active and reactive power, as it needs to maintain the grid voltage and frequency constant. As all of us know that the grid voltage or voltage profile at the point of common coupling essentially constant, and the frequency profile, it must be constant irrespective of the grid situation. So ultimately, the voltage profile can be maintained constant by injecting necessary reactive power. Yes, I can say necessary reactive power Q, and the frequency can be regulated by maintaining the active power balance. That is called active power regulation. So by having an independent active power and reactive power regulation, so we are able to maintain these two profile constant. Because, and all of us know that the power system reliability is largely depends on the voltage profile, whereas the power system security is largely depends on the frequency profile. So first important point is to meet while integrating is the controllable power that will be injected into the utility grid, and the grid synchronization with the improved power quality. And all of us know that the grid is an AC component, as power has to be injected at a constant frequency of 50 hertz. That is called a fundamental frequency. So that inverter output frequency must be well matched with the grid frequency. That is what is called the grid synchronization. So the grid synchronization with the improved power quality is very essential. In addition to, it has to influence on the grid stability when the grid is subjected to fault. As I mentioned, the renewable energy sources are basically the inertial system. It is difficult to provide any kind of damping to improve the dynamic stability of the system. Invariably, we use energy storage devices. And improved power quality, as all renewable energy sources are intermittent in nature, it always produces the power with variable voltage and variable frequency. And due to variable voltage and variable frequency, it inherently it generates a lower order and higher order harmonics. So due to that, harmonic components are injected into the utility grid, and it causes the power quality problem. So the one of the important grid connection requirement is to have an improved power quality with sinusoidal current injection of the utility grid, and quick response under transients in power system. Of course, the grid, it needs stability improvement. By that, we invariably uses energy storage. So these all 5 requirements are to be met for successful integration of renewable energy sources. right? So how can you meet these all 5 requirements? Invariably, we uses power electronics converter. So we uses power electronics converters between renewable energy sources and the utility grid, with power electronics converter with a suitable control strategy on the power electronics converter. Of course, we can meet these all the requirements. That is what basically these grid connection requirements are meant by a grid interactive power converter with a suitable control strategy, right? So while we use a power electronics converter between the renewable energy sources and the utility grid, it has to meet all the grid code requirements. But however, the following conditions should be met corresponding to voltage in RMS and measured at the point of common coupling. As far as the power quality is concerned, that voltage at the point of common coupling, when the voltage profile deviates between nominal voltage and 50% of the nominal, then the tripping time, the inverter should be tripped in 0.1 seconds. It implies 100 milliseconds. When the voltage deviations between 50 to 85%, then the tripping time would be 2 seconds. Then when the voltage variation is within between 85% and 110% of the nominal, then the inverter still it feeds power to the utility grid. When the voltage variation between 110% and 135% of the nominal, then the tripping time would be 2 seconds. When the voltage exceeds 135% of the nominal, then the tripping time would be 0.05 seconds. So it means we are instantaneously measuring these grid voltages, right? In addition to the voltage, when the utility grid frequency is outside the range of plus or minus 1 hertz, then the inverter should cease to energize the utility within 0.2 seconds. Please keep in mind that this point is very important. When the utility frequency is outside the range of plus or minus 1 hertz, the inverter must be disconnected from the utility grid within 0.2 seconds. Of course, it is about 200 milliseconds as far as IEEE 929/2000 standard it concerned for recommended practice for utility interface of solar PV system. So the inverter must be disconnected within 200 milliseconds. I mean, in it's about 10 AC cycles, right? So in addition to that, when the renewable energy or distributed generation system shall have an average lagging power factor of 0.9 when the output is greater than 50% of the load. So in addition to the previous requirements, this also has to be met. This also included the grid connection requirement. So to meet this all the requirements, what you wanted to do, you have to instantaneously estimate the voltage as well as instantaneously estimate the frequency, right? So thus the grid voltage and the grid frequency should be estimated and should be monitored fast and accurate enough in order to cope with the standard. So we are in a position to estimate the grid voltages and the grid frequency at every instant. Then based on the estimation of that fundamental frequency, we are able to employ a control technique on the inverter so that there is a successful integration of renewable power generation system, right? So the successful integration of renewable power generation system with the utility grid is possible by achieving grid code requirements, as I said in the previous slide. So hence, any grid connected renewable energy sources, including solar PV, that requires a fast and exact detection of phase and fundamental frequency. Please keep in mind that while you are proposing any control technique on the inverter, very first important requirement, how fast you are able to extract the fundamental frequency component. That is what is called 50 Hz component. The detection of phase and fundamental frequency of the grid voltages and currents to generate the reference current signal for implementing control strategy on the grid side converter. So in order to implement the control strategy, the reference current generation is very essential. So the reference current generation has to be done very precise way. That precise generation of reference current is possible by detecting the grid frequency or phase angle of the grid voltages. So a desired grid synchronization technique, it must detect the phase angle of the fundamental component as fast as possible while adequately eliminating higher order harmonic components. Because Invariably, inverter, it injects high frequency harmonic component due to non-uniform sampling frequency or non-uniform inverter switching. So while proposing any kind of grid synchronization technique for estimating fundamental frequency, basically they acts as a filter to filter out unwanted harmonic presence in the inverter output current or inverter output voltages. Yes. So the main objectives of the study is to develop a novel three-phase adaptive phase lock loop. It should be very simple and a very powerful grid synchronization tool for grid interactive PV system. With that, we can accurately estimate the phase angle of the utility grid signal and a smooth tracking of the phase and the frequency variations, and proficiently detect the current harmonics and extract active and reactive component of the grid current, because as you're proposing kind of vector control or decoupled control on the inverter to independently control the active and reactive power, and we have to detect the active as well as reactive current component. That is what we use as the symmetrical components. That is what is called a positive sequence component and negative sequence component. That has to be extracted in addition to detecting the current harmonics. And forcefully, it has to reject harmonic and disturbances to extract the symmetrical component. Forcefully, it has to reject all harmonic components present in the grid voltages. Right. So very fundamental technique, most widely used for grid synchronization, is that the phase lock loop. Because why we go with any controller on the voltage source, inverter or the grid interactive power converter, we always proposes the very fast acting digital controller. As we implement the control with the help of digital signal processor or maybe any microcontroller or maybe APGA controller, of course the control algorithm is in the digital form. Then the estimating the fundamental frequency possible with the help of digital phase lock loop. And you can see the analog phase lock loop as it has three important components called phase detector and loop filter and VCO. And what is the role of the phase detector is that as we feed the input voltage with the corresponding frequency, and this phase detector, it detects the phase difference between the actual phase and the estimated phase. And it is simply a comparator. It acts as a comparator. It compares the input and reference signal and it produces an error. That error is given to the loop filter. So the role of loop filter is to filter out any harmonic component or presence in the error signal, right? So to remove unwanted harmonics from the error signal, so that the filtered output voltage VO, that corresponding to the control frequency of the VCO. So VCO is what's called voltage controlled oscillator. Very fundamentally, phase lock loop is used in the communication system, especially for the frequency shift keying, especially on the digital communication we use as phase lock loop. The similar concept they use here for extracting the fundamental frequency of the 50 Hertz. So the voltage control oscillator is basically used to generate the output signal whose frequency varies around the central frequency that depends on the output of the loop filter. I mean, it is simply a voltage to frequency converter. What is the output voltage of the loop filter? The corresponding frequency will be generated is in the output of the VCO. When this frequency is in the same of the actual frequency, then the phase detector out the fundamental frequency of 50 Hertz. Yes, are you able to follow me, dear participants, please? Yes, please, let me know. Yes, dear participant, one can respond. Are you able to follow me?
Yes, sir.
Yes, sir.
Okay. Yeah, thank you. Thank you. Yeah, that is what. So the mathematical description of this phase locked loop or the functional description is available in this slide. You can understand that the phase locked loop is the input signal is A sin omega t plus phi. It is a fundamental input signal we are giving. You can see on the left corner, and the loop filter and this is the phase detector, and the VCO control voltage is available. The corresponding the cos component is producing that. Once the estimated phase and the input phase both are same, then the signal will be locked, right? So this is the corresponding mathematical expression of the phase locked loop. This is the phase detector and the loop filter and VCO. You can see the individual mathematical equations. So according to the mathematical description of the space locked loop, if the input voltage is not sinusoidal, yes, you can understand in the synchronous reference frame, as we feed three-phase input AC voltages, the function of PLL is to estimate the phase as well as the magnitude. So we are transforming this ABC coordinate into DQ in the synchronously rotating reference frame, and hence the name SR of PLL. And we are estimating the magnitude as well as phase of the fundamental grid voltages, as it has a D and Q axis component. The D axis component, it represents the amplitude of the grid voltage. Q axis component, it represents the theta, what is called the phase angle, right? And you can see the corresponding SRF PLL mathematical description. So we are finally estimating the value of fundamental phase. So the corresponding mathematical expression of this transformation, that is called ABC to DQ transformation, what is called the phase transformation, I mean the Clark transformation. At this stage, as for transforming this ABC to DQ, for converting, invariably we need theta, right? So that theta can be estimated with the help of phase lock loop, that we sense the grid voltages and the grid currents. So at near synchronization, so theta is becoming omega t. I mean, this is the fundamental phase, this is the fundamental frequency. But according to this, when the grid voltages are unbalanced, then you can see the sine omega t minus phi, you can take as it has a sine component as well as the cos component. From this, you can get the angular frequency in the form of -2. So this -2 is what is called a double frequency oscillations. It is what is called a double frequency oscillations. So now, due to double frequency oscillations in the grid voltages, now listen, the grid voltages are balanced, then phase locked loop can able to estimate the phase angle very accurately, so that the magnitude is 100 volt peak, and in the meanwhile, it is RMS, then the VSQ is 0. It is a -100 to +100 peak to peak. And when the grid voltages are unbalanced, then you can see the estimated phase is not so accurate. There is a deviation in the phase. So this deviation is due to the component what is called a double frequency oscillations. So the double frequency oscillations mean essentially a 100 Hz component. Due to this 100 Hz component, it is superimposed upon the fundamental. The estimated phase is not so accurate. Due to that, the amplitude of the voltages is oscillating. It is oscillating between -75 to +75. In the meanwhile, the Q axis component is not at all 0. So that is what the phase lock loop cannot be used for estimating the phase when the grid voltages are unbalanced. So across the globe, number of researchers, they have taken an attempt to detect the value of phase cycle very accurately during abnormal grid voltage conditions. Over 150 algorithms have been proposed in the recent literatures, including IEEE transactions. So from the conclusion from that literatures is that the features of good synchronization tool, the good synchronization technique based on the phase lock loop should have the following features. First of all, it should have a zero steady state error for the phase angle and for frequency variations. It has to efficiently track the phase and the frequency variation of the utility grid signal. It forcibly rejects third order harmonic and disturbances that exist naturally in the grid signal. Have good dynamic performance under grid voltage variations or frequency variations or during high frequency harmonic injection. In addition to that, it should be realizable in practice. So these are the important features of good synchronization tool. Any technique you can propose for grid synchronization, ultimately these all features must be accomplished with the help of proposed PLL or with the help of any new or any PL. So with that, what we have taken an attempt that when the grid voltages contain interharmonics, because number of algorithms are available in the literatures. They have proposed, they successfully implemented for estimating the phase angle or the frequency when the grid voltages are unbalanced, when high frequency harmonics are injected into the utility grid, when DC offset presence in the grid voltages, when there is a frequency variation, whenever there is a voltage set, for all power quality problem during for any power quality disturbances in the utility grid, they are successfully synchronizing the utility grid by estimating accurate phase angle. We have taken an attempt when the grid voltages contain non-integer frequency component. What is non-integer frequency component? Maybe the frequency between 50 hertz and 100 hertz, maybe 75 hertz. So the 75 hertz is basically what is called a non-integer frequency component. So such a frequency component sometimes may exist in the utility grid when you connect a load like any arc furnaces, or maybe any heavy induction motor drive with core saturation, or induction motor with a light loaded condition, that also can generate any non-integer frequency harmonic. So during such situation, when the non-integer harmonics are injected into the utility grid, how you are precisely estimating the phase angle. So we have been motivated by that scenario, and we have taken an attempt to estimate the phase angle. That was the first work I am going to present here, that to obtain the fundamental frequency to phase angle with a faster transient response, to attain very superior stability with the help of proposed PLL. And we have done a comparative investigation with the proposed as well as the existing PLL in the literatures. When there is a high frequency, non-integer harmonic components are injected into the utility grid, and still we have compared with the different power quality event like a voltage sag, high frequency harmonic injection, and DC offset, and frequency variations as well, to show the efficacy of the proposed PLL. And we have made the laboratory setup as we could be able to develop an algorithm in the MATLAB Simulink, as we are able to generate the PWM pulses with the developed mathematical algorithm in the MATLAB Simulink that we used in the DSpace 1104 control card. So we could be able to do in the hardware in-loop environment, that is called HIL simulation, so that we could be able to validate all the results. You can see the schematic diagram of grid connected solar photovoltaic. A solar PV array it generates a DC power, as this has to be injected into the utility grid via power electrons converter. It consists of a two-stage power converter system. Two-stage power converter means DC to DC boost converter, three-phase voltage source inverter. Both are perfectly decoupled with the DC component by a DC link capacitor. And the boost converter basically it interact with the source or the PV array to extract maximum power by proposing a maximum power point tracking. Then the power available at the DC link, that will be transferred to the utility grid via three-phase voltage source inverter. Basically, this is what is called grid side converter or grid interactive power converter. And this fellow is responsible for successful integration of solar PV with the utility grid, as it feeds power to the utility grid, that is called controllable active power and controllable reactive power via interfacing inductor, and we have interfacing transformer as well. So we sense the three-phase as we connect a nonlinear load at the point of common coupling, as we sense the three-phase voltages, and we are proposing a advanced phase locked loop or the proposed PLL. So we are estimating the value of theta and the frequency. So with that, we are sensing both voltages as well as current, and we are able to generate the current references. Then as the current references that we are generating then you can have a grid side converter controller, and it is able to generate the PWM pulses by comparing actual grid current and reference grid current. Then it will activate this all IGBT transistor switches and the voltage source inverter, so that we are able to implement the control algorithm. So simply grid synchronization means generating the reference current. How precisely you are able to generate the reference current, that shows the superiority of your control algorithm. Yes, and the algorithm what we proposed for estimating the value of theta when interharmonics are present in the utility grid, we could study about the sliding Gaussian discrete Fourier transform based PLL, because our intention is to estimate the fundamental phase angle and the frequency of the three-phase AC voltages. And you can see here, and this is what the PLL actually, this part is actually what is called a phase lock loop, And this has been realized in digital domain. That is what it is called, a digital phase locked loop, or we can say it is called a ADPL, all digital phase locked loop. So before this phase locked loop, we have a AGTFT before this PLL, and hence this is what is called pre-filter. So this act as a pre-filter. This act as a pre-filter. So because when the grid voltages are unbalanced or balanced, then we are transforming into alpha beta. Then we have a V alpha and V beta. Then we are having AGTFT filter as a pre-filter. This will filter out the harmonic component or the error signal presence in the signal. Then we are feeding actual grid signal to the phase detector. Then it is successfully integrating, right? So the corresponding discrete transfer function of the AGTFT PLL is available in the form of Y of Z and X of Z. You can see here. And for this AGTFT PLL, this is the structure that the actual grid signal, and we have a comparator with Z minus N. It is what is called unit delay. So that is act as a comp filter. Because this comp filter, what this fellow it does, this fellow make the unit delay and the grid voltages so that it is able to segregate the input voltages with or without any non-integer frequency component. Then after we have the signal here, and further we have a unit delay in the form of signal. Then we are getting both, I mean, a real and imaginary part. This is the corresponding transfer function. And they were 1 minus z to the power minus n is the unit delay with the comp filter, as where n we take 128 samples corresponding to the frequency of fundamental 50 hertz. So fundamental 50 hertz means then sampling frequency for the D space, it should be 128 and 50, it's about 6.4 kilohertz. That is what we have taken 128 samples corresponding to the frequency index of K is equal to 1. And we analyze this filter, that is AGTFT based filter with the Lagrange interpolation method to understand the unit delay in the comp filter. And this is a corresponding the mathematical expression for that. And we could make the analyze as we made the modified AGTFT PLL here. This is what the modified AGTFT PLL that we could make in the next, as we have added that the number of filters is n is equal to 1 or n is equal to 2 or n is equal to 3, as we have taken with a different gain component G of 0, G of 1, G of 2, G of 3, and the magnitude response of the second order fraction delay when n is equal to 2, that is the dashed line, it is closer to unity magnitude when d is equal to 0. You can understand that this is what the unity magnitude. And when you take n is equal to 1, the dashed line exactly converges with the unit magnitude. So the magnitude of fraction delay in the third order, when n is equal to 3, then the dotted line means the unit amplitude, which may possess a stability problem. You can see this is what corresponding to when n is equal to 3. You can see here it is n is equal to 3. So the third order fractional delay required more multiplication as well as addition operations with the second order fractional delay. So we have taken second order fractional delay is introduced to the Lagrange interpolation method so that it shows the characteristics what is called the band pass filter characteristics. Yes, you can see as we are adding the delay, this is the actual AGTFT filter. We have added two more filter, that is called a second order delay with this additional comp filter, so that your AGTFT filter is modified. That is called AGTFT, modified AGTFT filter as a pre-filter. Then this is what the actual output in the form of real and imaginary. And this was the novelty in that we have added the second order unit delay with the Lagrange interpolation method. We could develop a modified AGTFT filter that we have proposed, so that we could make a paper, and we published in IEEE Transactions and Instrumentation and Measurement, that is available online. And each component of the AGTFT filter, that is called moving average filter and PI controller. And this is what the stability. So the very important thing in the phase locked loop, how fast it is estimating the fundamental phase angle, that it depends on the dynamics of the loop filter. That is called the PI controller, at what we use as the loop filter. That is essentially important. It shows very stable when the grid voltages are unbalanced. So that is what we have taken the stability of the PI controller with a different value of the gain, as we have taken symmetrical optimization method. We tuned the value of controller and we could be able to see the value of the PI controller gain, PI proportional and integral gain. So for the corresponding gain, how the system it shows the stable. Here, this zone is unstable and this zone is stable region. So it states that design of PI controller must consider omega f by omega ratio. Here omega f is the cutoff frequency that should be higher than the value according to the reference 25. Moreover, this plot indicates that the Ki, that is the integral gain towards the destabilization. That is what here you can understand that. And it shows the stability. This is the numerical control oscillator, the equations. And for the modified AGDFT filter, and we could be able to take both real and imaginary component in the digital domain, it is available. So we have implemented this in the what is called in the discrete form, so that we could make the the stability and the frequency response of the filter. This is very essential. While grid voltages are unbalanced, you can see that this is corresponding to the fundamental frequency 50 hertz, 150 hertz, 250 hertz, 350. Now there is a frequency range between 50 and 150. This is what is called a non-integer frequency component. You see the different PLL that available in the literature, it can detect the value of phase when the frequencies are integer multiple of fundamental, but the existing PLL unable to track non-integer frequency component called interharmonics. But the red is the proposed PLL. It can able to detect even non-integer frequency component. You can see it is detecting, and correspondingly the phase angle it is becoming 0. So as we took 128 unit circle in the pole 0 plot, and the two poles are placed on the unit circle, so it shows that the PLL is very stable. The extraction of the single frequency component produces two poles that cancel mutually with each other. So we have taken n-2 two zeros equisitely spaced in the unit circle, so that the proposed PLL or modified AGTFT based PLL, it remains stable irrespective of the grid voltage conditions. And we have designed this PLL in the MATLAB simulator considering the peak voltage of 1 per unit, and the fundamental frequency is 50 hertz, and the angular frequency is about 2 by f. And we have taken 128 samples corresponding to the sampling frequency of the DS1104 DSP card, that is 6.4 kilohertz, and the enabling frequency is about 25.6 kilohertz according to the NCO. And we have done the simulation in the MATLAB simulator, as we have created the voltage sag between 0.4 to 0.5. So we have created 30% of the voltage sag between here. You can understand how the proposed PLL as well as the existing PLL can estimate the value of frequency 50 hertz. You can see here PLL, it is completely estimating the 50 hertz. When there is a changes in the frequency, changes in the grid voltages, still it is able to track. But rest all, it shows there is a steady state error as well as peak overshoot. You see the phase error. It's the blue line is for the proposed PLL. It is completely 0. But for other PLL, there is a steady state error. When there is a step change in the MAC, that is what that voltage sag at a 30%. It is how fast it is tracking the reference, but it is having negligible steady state error. And this is for the high frequency harmonic injection, as we are injecting 33% of the third harmonic, 25% of fifth harmonic, 17% of seventh order harmonic, and 13% of ninth order harmonic, and 8% of the 11th order harmonic between 0.4 and 0.5. See the response. The proposed PLL, it is exactly detecting the fundamental frequency as well as the fundamental phase. And this is the response under interharmonics. So during interharmonics, as we are injecting 8% of 5.5 fifth harmonic and 4% of 7.5 harmonic interharmonics between 0.4 and 0.5. But see, the blue is the proposed PLL. It is exactly detecting the fundamental frequency, and the error is almost 0. It is and this is under DC offset. When the DC offset or the zero frequency component is injected into the utility grid, about plus 5% in the A phase and -3% in the B phase and -2% in the C phase. You can see how it is able to track the value of fundamental frequency, and it is exactly detecting with negligible steady state error, and it is accurately tracking the value of theta. So that we could make in the D space DS1104 controller card in the hardware loop, and we have analyzed this setup in this. You can understand during voltage sag, it is exactly detecting. You can see the steady state errors as well as the peak overshoot. It is exactly detecting. This is HIHDO PLL. This is PFS PLL. This is HGTFT PLL. This is modified HGTFT PLL. So the error is less as compared to the existing PLL. And you can see the peak overshoot are reaching the steady state. It is the HIHDO PLL is taking about 60 milliseconds. And HP's PLL is taking 32 milliseconds, and AGTFT PLL is taking 40 milliseconds. But the proposed modified AGTFT, it has a zero delay while tracking the fundamental frequency as well as the fundamental phase. And this is corresponding to the high frequency harmonic injection. As we are injecting into the utility grid, it is tracking the value of phase very accurately. Before tracking, you can see the unit vector template, they are distorted due to high frequency harmonic injection, but it is filtering out all high frequency harmonic components so that it is estimating the fundamental phase very accurately. And you see the phase error, it is tracking the fundamental of 50 hertz very accurate. This is what the modified HGTFT PLL, it does not have any. You can see the error corresponding, but here there is no error, and the corresponding THT is also about 3.0%. It implies grid voltages are almost sinusoidal. And this is the result during interharmonics. As we are injecting the interharmonics between 0.4 and 0.5, see, it is tracking the value of theta very accurately, and there is no error. This is the very important novelty in that modified HGTFT PLL, that during interharmonic presence in the utility grid, it can extract the fundamental component very accurately with negligible steady state error, with reduced peak overshoot, with the THT of 2.3% of the grid voltages. And this is the result during DC offset. When the zero frequency harmonic components are injected into the utility grid, still it is meticulously tracking the value of theta, and also it is tracking the both the unit vector template called sin theta and cos theta component for reference current generation. You see the error is almost zero. It is detecting the fundamental frequency of 50 hertz, but there is a considerable error in the existing phase lock loop. The THT is largely reduced to 0.5%. Right, you can see the comparison between the different PLL for the different power quality, even to voltage sag, interharmonics, and high frequency harmonic injection and DC offset condition. And you can see for the different state of art of the PLL as well as the proposed PLL, you can see the improvement and the superiority of the performance of the proposed PLL. That is what we could show the novelty and the improvement in the response of the digital filtering for the phase angle detection with the help of modified HGTFT PLL that we could be able to make in IIITDM transactions. This was the work, and we could make that the modified HGTFT PLL is designed as it uses 3 degrees of freedom. That is what is called, we use the second order fractional delay using Lagrange interpolation method, as we could make for extracting the fundamental when harmonic, non-integer harmonic components are injected into the utility grid at a fixed sampling frequency. The fundamental frequency from the distorted grid voltage and current, it can be easily eliminating the harmonics, interharmonics, and DC offset as well. And the modified HGTFT PLL, it largely reduces the frequency overshoot. It is very important as far as the dynamics of the utility grid is concerned. Tracking the value of theta when the grid is under fault, it's a challenging task. Still, we haven't taken in any attempt to estimate the value of fundamental phase when the grid is subjected to unsymmetrical fault. That is what. So the reducing the frequency overshoot is a very important function of any phase lock loop. Right. In addition to the settling time, and also the validation that we have done in the MATLAB simulating, in addition to hardware or HIL loop simulation that we could make. So another important algorithm detection when the frequency variations are very wide in the utility grid. So that for that we have proposed adaptive band pass filter based pre-filter for grid synchronization under distorted grid condition, especially during frequency variations. So we have taken an attempt to estimate the value of theta when there is a wild variation of the grid frequency component. So this may happen when the grid is subjected to highly nonlinear load connected at the point of common coupling, and also the frequency variation is very wide when grid is subjected to unsymmetrical fault. Sorry. So that was the study we have made, and we could publish that paper again in IEEE transactional instrumentation and measurement, and you can have a look at this paper and you can read, you can understand the complete ideology of this proposed PLL. Right. So there was a paper in the literature, it is based on adaptive low pass filter. So this adaptive low pass filter, again it is a pre-filter. You can see it, this is the PLL. With the help of the PLL, we are estimating the fundamental phase and the fundamental amplitude. But the before PLL, we use this filter as a pre-filter. So that is what this is. Again, it is basically a free filter. Again, it is a pre-filter. So we have, it is basically an adaptive low pass filter. So we feed input voltage to the low pass filter, and the error is again, it is summing with the actual signal. Then what is the corresponding output from the PLL, and again we are feeding back to the LPL. So we are trying to make this LPF must be adaptive in nature whenever there is a variation in the fundamental frequency. That is what it is called adaptive. But as we use as a low pass filtering, it allows to pass only low frequency component like a fundamental frequency component, and it is trying to make the system is very adaptive. This is the corresponding discrete implementation of adaptive low pass filter, and we are estimating the amplitude as well as the phase angle corresponding to the input grid voltages as to estimate the DC offset, and the input signal is passed through the first order low pass filter, and we have the corresponding low pass filter transfer function. As we need to get the it is called a distortionless input signal from the summer. This is what the distortionless. So the estimated DC offset component, it is subtracted from the Vin, right? Then the corresponding transfer function is available in this equation. That is what feeding to the phase locked loop. So these two transfer functions corresponding to pre-filters. Now, so in the corresponding, the magnitude as well as the phase angle corresponding to the previous two equations, it is in both in analog domain as well as the discrete implementation. You can understand the transfer function as we plotted the phase lock, the frequency plot for this, that body plot of adaptive low pass filter, which allows the particular signal based on the cutoff frequency, right? At a particular frequency is what is called the fundamental frequency, as we are trying to find the magnitude as well as the phase plot corresponding to -3 dB and to -45 degree respectively. But when the high frequency harmonics are injected, or when the grid frequency variations are very wide, it is unable to track the phase angle, and it shows negligible. It shows there is a significant overlap in the steady state error as well as in the frequency overshoot. That is what, to mitigate or to improve the performance of adaptive low pass filter, and we have proposed an adaptive band pass filtering, as it has a capability to allow the frequency within certain band. That is what it is called adaptive band pass filter. So if the input frequency is a fundamental of low frequency, and still if the frequency component is less than 50 Hz, what is called a subharmonic component, still it can able to track only the fundamental frequency component. But adaptive low pass filter cannot able to eliminate a subharmonic component. It allows only the fundamental frequency component. Pre-filter for any kind of phase locked loop, as we have adaptive band pass filter as a pre-filter. Then we have ABC to alpha beta and alpha beta to DQ transformation, so that we are estimating the magnitude as well as the phase angle. This is the system of the adaptive band pass filter, as we have the characteristics of the band pass, as we have in loop filter PI controller, and we have the VCO based on the cutoff frequency. Then we are estimating the value of theta by integrating the cutoff frequency, right? As we have a VA, VB, VC are basically a three-phase AC voltages. Then we are converting that ABC into alpha beta in the stationary reference frame, and in terms of VQ, and further we are getting VQ VB, that is in terms of V alpha V beta, and in terms of sin theta cos theta common. So this generation sin theta cos theta, it needs to estimate the value of theta. For that we are sensing grid voltages as well as grid current. That is what we need, actual sensor and the utility grid. From the CTPT, we have to have a Hall effect sensor so that we are able to sense the grid voltages and current. And further, we are converting that analog components into digital component. Then the digital components are going to be processed. That is what these all PLLs are realized in the digital domain, and hence this loop, this PLL is what is called all digital phase locked loop. That you please keep in mind that. Okay, and as the corresponding to the power transformation of the adaptive bandpass filter in the form of ABC to alpha beta, we have the VQ and VD component. Q component is corresponding to a magnitude, and D axis component corresponding to the phase angle. This is the corresponding discrete implementation, and we are estimating the real and imaginary. So we are trying to find the continuous time of bandpass that is available here with binary transformation. After subtracting, we are getting the value of S in the form of Z domain, and we are trying to find the transfer function. So using this transfer function, we are plotting the frequency response of the filter. As I mentioned earlier, the filtering response is very essential for any phase locked loop. How fast or how quickly it is able to track the value of fundamental phase and frequency. That is what. So the filtering characteristics are very important. So we could observe the frequency response of the adaptive bandpass filter and corresponding to the root locus of the or the body plot, as well as corresponding to the port zero map of adaptive bandpass filter for the different value of K. That is what the gain value. You can understand that the K value to be considered very low for the desired bandwidth of the phase locked loop, first of all. And as for the frequency of the for fundamental 50 hertz, the free filter magnitude phase angular 0 dB and 0 degree respectively. You can see here it is 0 dB and 0 phase respectively for the corresponding fundamental 50 hertz. So it implies the frequency or the filtering characteristics is very good. And for the different value of K, we are plotting that the poles are on the left half of the S plane. According to that, it indicates the system is guaranteed system stable, and moreover the complex factor K from 0.5 to 1.414, so that we are able to see the dynamic stability as we are plotting using the stability boundaries for the adaptive bandpass filter. These stability boundaries are corresponding to PE controller in loop filter. So the PE controller gain that we could be able to evaluate using symmetrical optimization method, and we are seeing the stability boundaries for different integral as well as derivative gain, integral as well as the proportional gain. So then we are observing the stability boundaries. This is the stable operating region where the blue is, and this line beyond it's in the unstable region. So that you go to tune the PA controller in such a way the PLL or the adaptive bandpass filter source remains stable when the grid voltages are unbalanced, or when the grid is subjected to uncertainty. Maybe there is a certain harmonic current injected into the utility grid. So how PLL did response? That's why this response time is always calculated in terms of milliseconds, because the fundamental phase or fundamental frequency of 50 hertz corresponding to one cycle of AC wave, it's about 20 milliseconds. That is what the response time should be calculated in terms of milliseconds only. And here, what we have studied, we have taken this adaptive bandpass filter that can be added as a pre-filter for any existing phase lock loop available in the literature. So one PLL is called DQ-CDAC PLL, moving average filter based PLL. So we have added this adaptive bandpass filter as a pre-filter for DQ-CDAC PLL and moving average filter based PLL, and that we have implemented here. This is the schematic diagram of adaptive bandpass filter based PLL for DQ-CDAC PLL. This is the corresponding discrete implementation, and this is the PLL for adaptive bandpass filter based PLL of moving average filter PLL. And here we are adding the pre-filter of AB. This is the corresponding discrete domain. So this adaptive bandpass filter PLL can be used as any pre-filter for any kind of PLL. Whatever with the PLL, for example, SOGA PLL, what is called a second order generalized integrator PLL. You take that PLL. So then you use adaptive bandpass filter PLL as a pre-filter. So it improve the overall system performance. Right. So we have implemented this adaptive bandpass filter based PLL for DQ CDSC PLL, as well as we have taken for the PLL what is called the moving average filter based PLL, and we have compared with the different structure of the PLL. Then we have done the study. As we could take 415 volt, it is a line to line RMS as a 1 per unit, corresponding to the fundamental frequency of 50 Hz. And the Kp and Ka gain that we have calculated about 445.46 for proportional gain and 38.25 for integral gain using symmetrical optimization method. You can see the response of the adaptive bandpass filter with the DQ CDSC PLL as well as the moving average filter PLL, both low pass as well as bandpass. And you can see here 1, 2, 3, 4 PLL we have compared, and sir 1, 2, 3 PLL we have compared, and you can see when the time between 0.4 seconds and 0.5 seconds, and the frequency variation is from 50 to 51 Hz till 0.7 seconds. So till 0.7 seconds the frequency is varied from 50 to 51 Hz. So how your the different PLL can able to follow the reference frequency that is called a 51 Hz, how it is able to track. You see, and the blue line is the proposed PLL. It is reaching the steady state as quick as possible, and moreover accurately tracking 51 Hz component. But this red line is a DQ CDSC PLL with adaptive bandpass. It is taking time. Of course, the steady state error and also the settling time is larger. And the green is a moving average based PLL. Still, the response is very sluggish. And you can see the corresponding the phase error. You can understand how beauty of the blue color that is exactly following the reference, and the frequency error, and how fast it is tracking the value of phase angle. Right, this is for the frequency variation. This is during high frequency harmonic injection. So we are injecting for 33% of third order harmonic component and 25% of fifth order harmonic, 17% of seventh order, and 13% of ninth order, and 8% of 11th order. We are injecting between 0.4 and 0.7. So how the response with the different state of art of the PLL, you could see that it is estimating the value of theta very accurately. So it reduces both steady state error as settling time as well as the peak overshoot. And this is during interharmonic conditions when high frequency non-integer components are injected into the utility grid, about 8% of 5.5 harmonics and 4% of 7.5 harmonic injected into the utility grid till 0.5 second, and how the PLLs are responding for extracting the value of fundamental phase. And you can see here between 0.4 and 0.5, the proposed PLL, that is what the blue, it is showing the negligible error. It is exactly tracking the value of fundamental frequency of 50 Hz, and it is rejecting all non-integer harmonic components present in the utility grid, and also the phase as well as the frequency errors are completely zero, and it is tracking the value of theta very accurately. And this is the response during DC offset. So during DC offset, as we are injecting plus 5% of the DC component in the A phase and minus 3% of a DC component in the B phase and minus 2% of DC component in the C phase yield till 0.5 seconds. So now you see the proposed PLL is a blue. It's exactly tracking the fundamental 50 Hz. There is no phase error. There is no frequency error. It is completely following the reference of the 50 Hz. And it is exactly tracking the value of fundamental phase during DC offset. And this is what the condition during unbalanced grid voltages. And this is mostly the grid is under unbalanced as we connect a highly non-linear electronic load at the point of common coupling. This is the natural tendency of the grid, that the grid voltages are always unbalanced. So during such situation, how the proposed PLL can able to track the fundamental frequency of 50 Hz? and can able to track the fundamental phase. You can see here, during such unbalanced three-phase voltages having a different magnitude of A phase, B phase, and C phase, till 0.6 seconds, you see here the blue is the response of the proposed PLL. The phase error is completely zero, and but there is an oscillation in the DQ-CDAC PLL as well as moving average filter based PLL. And see the phase error as well as the frequency error, but the estimated phase is so accurate for the proposed phase locked loop. And this is the corresponding hardware results in the HIL simulation. It's not an experiment, it's a hardware HIL hardware results. And you can see when the three phase, the frequency variation is there from 50 to 51 hertz, and how it is tracking the 51 hertz component, and see the peak overshoot as well as the settling time. Settling time, it shows only 38 milliseconds for the proposed adaptive bandpass filter based moving average filter based PLL, but adaptive low pass filter based moving average filter PLL response time is about 46 milliseconds, and moving average filter based PLL, it is about 60 milliseconds. This is corresponding to the estimated frequency with the DQ-CDAC PLL, and this is the adaptive bandpass filter based DQ-CDAC PLL. The error is reduced, and moreover settling time is largely reduced. And this is adaptive low pass filter based DQ-CDAC PLL. Still, the error is more, and moreover settling time is quite large. And for DQ-CDAC PLL without any adaptive low pass, any pre-filter, still the error is more. You can see that 22 hertz, the frequency error, frequency overshoot, as well as the settling time is about 82 84 milliseconds. See the corresponding phase angle by proposed phase locked loop, and you are meticulously generating the unit vector component, that is called the sin theta and cos theta component. So these two component generation is very essential, because with this unit vector template you are able to convert or transform ABC components into DQ synchronously rotating reference frame component, or ABC into alpha beta stationary reference frame component. So this is what is called the unit vector template generation. So that is also the role of phase locked loop. Yes, this is what the response during high frequency harmonic injection, as we are injecting high frequency harmonics in the utility grid, and see the response or the tracking the fundamental phase. And this is the proposed PLL, it is exactly detecting the fundamental 50 hertz, but the adaptive low pass filter based moving average filter, still it shows there is a phase error. And this is the response with the DQ-CDAC PLL, and this is the DQ-CDAC PLL with adaptive low pass. This is the DQ-CDAC PLL with adaptive band pass. So here there is no error. It is tracking the phase very accurately. Moreover, it reduces the THD according to IEEE 519/2014 as well as IEEE 929/2000 standard, that meant for recommended practice for the utility interface of solar PV systems. Right. And this is the response during interharmonics, as we could take an attempt for estimating the phase even during interharmonics, also with adaptive bandpass filter as a pre-filter for DQ-CDAC PLL as well as moving average filter based PLL. This is the response of moving average filter PLL with adaptive low pass filter, and we compared with the adaptive bandpass filter based moving average filter PLL. And this is the attempt for DQ-CDAC PLL with adaptive bandpass filter, adaptive low pass filter, simple DQ-CDAC PLL. So overall, you see the performance of the proposed PLL is very superior as compared to state of art of the PLL. Right, estimating the theta, estimating the fundamental frequency is so accurate and so fast, it largely reduces the settling time as well as frequency overshoot, and also it is able to track the fundamental phase with negligible total harmonic distortion of the grid voltages. So ultimately, these proposed PLLs are not only utilized for extracting the fundamental frequency at the phase angle, this also can be used for grid monitoring. In the large spectrum of the grid integration, this also can be used for grid monitoring and power quality improvement, or power quality improvement by reducing or filtering out the harmonic components presence in the utility grid. With that, we are able to implement the control algorithm on the grid interactive power converter, so that the successful integration of renewable power generation is possible. This is the result during DC offset, as we are injecting a zero frequency harmonic component with the different phases, and you can see the response. The proposed adaptive bandpass filter based moving average filter, it is tracking the value of theta, frequency very accurately, but here there is a error with adaptive low pass filter, and this is what the adaptive bandpass filter with the DQ CDSC PLL tracking the frequency very accurately. But the DQ CDSC PLL with adaptive low pass, you can see the error, and the DQ CDSC PLL simple PLL, you can see still the error is more. So it is unable to track the frequency when there is a DC offset injected into the utility grid. And alternately, it is able to track the fundamental phase angle very accurately, and also it is able to generate sin theta cos theta component very meticulously. Moreover, these two components must be orthogonal to each other, so that we can have a possibility of independent control of active and reactive power. Because the independent control of active and reactive power is very essential for independently control the utility grid voltage and utility frequency as well. Right. So this is the response during unbalanced grid voltages, as we connect mostly a nonlinear load at the point of common coupling. This is the nature of the grid voltages under unbalanced. Still, the adaptive bandpass filter based PLL with moving average, it is tracking the value of frequency. But here there is a considerable amount of error in the settling time as well as in the frequency overshoot. And here you can see the visualization of the frequency error with the DQ CDSC PLL and adaptive low pass filter based PLL, but adaptive bandpass filter based PLL, the error is completely neglected. So by that, it largely improve the tracking performance of the estimated phase angle as well as the sin theta as well as cos theta component or unit vector template. So this is the comparison table with the different state of art of the PLL, that is the DQ CDSC PLL that has been proposed in reference 7. This is moving average filter based PLL in the reference 8. Here, adaptive low pass filter can be added as a pre-filter for DQ CDSC PLL in the reference 28. Here, adaptive low pass filter based PLL that has been implemented for moving average filter based PLL in reference 23. This is the adaptive bandpass filter based DQ CDSC PLL. This is the proposed PLL, and this is the adaptive bandpass filter based moving average filter PLL. So this is the performance of the proposed PLL. These PLLs can be added as a pre-filter for any kind of PLL, and see the comparison for different power quality even, including frequency variation, high frequency harmonic injection, interharmonics presence in the utility grid, and DC offset current injected into the utility grid. Overall, the performance is very superior. Understand from this work that the meticulously estimating the value of phase angle and the fundamental frequency is a very vital in grid integration of renewable power generation system. So it doesn't mean that as we uses the energy storage in addition to existing renewable power generation integration, it is possibly improving the overall system performance. Of course, integration is possible with a sophisticated and the robust control technique that will be implemented on grid interactive power converter. So for implementing that robust control technique on the inverter, the reference current generation is very essential. That reference current generation is very essential is possible by estimating the value of phase very accurately. That is possible by proposing a phase locked loop. That was the work and we have done, and I could be able to explain here for this particular session. So we proposed that adaptive bandpass filter can be added as any pre-filter for any PLL structure to extract the fundamental frequency and the phase angle. Moreover, for showing the adaptive bandpass filter is very adaptive in nature, and we have done that the center frequency is auto-adjusted using a gradient algorithm for various distorted grid conditions, as we have shown the 3D plot for the stability region of the PI controller. Accordingly, the P and integral gain are tuned based on symmetrical optimization method. As we have done the complete algorithm on the MATLAB sibling further, that has been validated in the hardware in loop environment in the laboratory prototype with the DS1104 platform. Right. So further, from the study, what we could see that the recommended PLL can be used as a pre-filter for any PLL structure to adequately eliminating the harmonic component and interharmonic component and DC offset mitigation with reduced settling time and reduced THD as per IEEE 519/2014 standard. Of course, these include the grid connection requirements of solar PV system or wind energy conversion system. Likewise, the proposed PLL that provide improved stability and the fast dynamic response. Right. And as we have concurrently, we have done the comparative study as we have added this filter as a pre-filter for DQ-CDAC PLL as well as moving average filter PLL. So we have compared with adaptive low-pass filter based DQ-CDAC PLL and adaptive low-pass filter based moving average filter PLL and DQ-CDAC PLL and moving average PLL with adaptive bandpass filter for the different power quality event, including frequency variation, harmonic injection, interharmonics, DC offset, and unbalanced grid voltage conditions. Right. And this was the references we could see the problem the formulation in this particular area. These are the reference paper as we have taken from the IIITDM transaction for the effective comparison. So we could show the novelty in the proposed work that has been made as a research paper in IIITDM transactions. Okay, so hope you all might have understood about the importance of grid synchronization. So how the grid synchronization is possible by proposing any kind of adaptive filters that can be used as a pre-filter for any PLL structure, so that we are able to meticulously estimate the fundamental phase angle in the frequency of the utility grid, so that there would be a successful implementation of the control technique on the inverter. So ultimately, we can integrate any renewable power generation system with the utility grid. So possibly this kind of PLL technique, it's moreover, please never feel that this is the kind of new concept. Since the inception of the renewable energy, renewable energy establishment since 1980s, so they could use this kind of algorithm. Very first, this has been floated for reference current generations in the induction motor drive, and wherever we used to estimate the speed, that is what is called the rotor position, we use the PLL along with the sensor, and further the PLL can also be used in the active power filters for reference current generation. That has been further extended to switch mode power supplies for the converter and the closed feedback. Further, this also can be used in the renewable energy integration. Of course, now it is in a very emerging now, the electrical vehicle integration, that is called the plug-in electrical vehicle, is also a challenging task. So for that also we can use this kind of algorithm for implementing the control strategy on the inverter. And we go to use the closed loop control. For implementing control, we need to estimate the phase. Via estimating the accurate phase estimation, we could be able to generate the reference current very accurately. Right. So hope you understand about the grid synchronization, how this is possibly done with the help of different digital filtering technique like adaptive bandpass filter or modified AGDFT filter. So understanding and implementing this kind of technique for renewable energy systems, of course, one should have an understanding and the foundation in the signal processing. Of course, this is a kind of technique very first in the classical power system they used for the frequency estimation or power quality events classifications in the classical power system. Then further that has been extended for renewable energy systems as well. Okay, so thank you all for your kind attention. So if you have any doubt, please let me know. Yes, please.
Thank you, Dr. Chitti Babu. And
yes, sir. Thank you, sir.
It was really a nice interaction on phase locked loops. So if any student is having query, he can ask the queries related to PLL or associated aspects of PLL.
Hello.
Yes, please.
Sir, good evening.
Yeah, good evening.
Sir, I have two queries.
Yes, please.
Sir, first one is in initial slides, you have discussed the different gain values of PI controller.
Yeah.
So I have a query. Have you used different value in your system, or you have used single value? If you have used different value, how you manage these values in this system?
Yes. It's yes. We have taken different power quality event like high frequency harmonic injection, frequency variation, DC offset injection, and interharmonic injection, as well as the grid unbalances. Yes, as you are finding a gain of the PI controller for a particular event, right? So that the gain what we were showing, that is usually 90% of 95% of the grid always under unbalanced grid voltages. So that we have taken for that particular case study. So similarly, while high frequency harmonics are injected, then the gain of the controller should be tuned accordingly, and again that has to be made for the stability. Understand? So the gain cannot be the same for entire kind of entire power quality event. For further, if the grid is under subjected to fault, again tuning the PA controller, again make it very adaptive. That is again it's a challenging task.
So, sir, is it considered in this work or not?
Yeah, that is what the grid fault is beyond the scope of the work, as we haven't taken in any attempt. But as further we are extending this work to the grid fault condition, but it is a really very challenging task, because when the grid is subjected to fault, restoring the energy itself is a challenging task. Invariably, we need energy storage. In the meanwhile, the fault can be cleared in the short follow-up time, maybe within 10 to 20 AC cycles. So during that, taking the sampling time, again tracking the fundamental frequency is very challenging task that we haven't taken in any attempt. That we have taken abnormal grid voltages considering these case studies.
Okay, sir. Sir, I have another question. Sir, as in your maximum results, you have compared your method with two another method. Means you have compared 3 methods. So my query is that generally we very well know the parameter of our method. Whatever we are proposing, we are familiar with that. But while we are comparing our method with existing method, it is a typical task to get the exact parameter, or we can say is that parameter are okay or not. We are not sure. So how we are expecting that method? My question is that.
That is what, see, you are comparing the PLL bin. Of course, we are familiar with that PLL also. So we have developed that mathematical algorithm for that PLL also. We could test the case for the different case study. Then we understood there was a problem associated with that. Then that problem can be encountered with the help of proposed PLL. That is what. So the research, it meant that the existing study we are taking for the comparison. Yes, I am agree with you that someone might have proposed an algorithm for a DC offset injection. During such case, maybe the frequency overshoot can be largely reduced as compared to the proposed PLL. It can happen. But we cannot compare all the PLL, whatever are available in the literature. That is what I told. Over 150 PLL, different PLL structures are available for grid synchronization. So how could I compare this all 150 exists data part of the PLL with the proposed? Of course, one PLL may fail to show the efficacy maybe during DC offset. But one PLL can show the efficacy during DC offset injection. So that is what it is, right? So our study is limited to take the recent literatures for the comparison. That is what we used to do usually. Understand, right?
Yes.
So hope you understand. Yeah,
yes,
understand that.
Because
see any comparison. So we even while reading any very older article, maybe during 2000 or 2002 article that have been published in IEEE Transaction, still it shows the great impact on the research. But usually the research community, what we expect for the novelty, we used to refer the very recent literatures for the effective comparison. So that is what we used to take the very recent references available in the IEEE transaction. So we have made the comparisons. But I cannot, assure that the proposed PLL is excellent in all aspects as compared to all state of art of the PLL, right?
Yes, that's it.
Yeah.
Thank you, sir. Thank you, sir, for opinion.
Yeah.
Any other participant? If you have any query.
Sir, good evening, sir.
Yeah, good evening.
Sir, at what range PLL can be maintained the locked at the circuit?
That locked in range, it has a different characteristics as far as communication system is concerned, as far as the power system is concerned. Here we largely work with the power frequency of the 50 hertz. So locked in range means we never assume that the grid voltage is always sinusoidal and balanced, right? That is what we are tracking instantaneously, the grid voltages. Then we are trying to feed to the PLL so that it is tracking, it is able to track only the fundamental frequency. But at what range this the frequency that signal is going to be locked, that we cannot see as it is a power frequency range. Understand? But if it is in the analog or if it is in the digital communication, especially for frequency shift keying or the phase shift keying, you can able to maintain the lock-in range, because that is exclusively for estimating the particular communication frequency range. So that may be the important attributes in the communication system. For the power system point of view, we mostly discuss about dynamics of the PLL. So the tuning of PI controller is very essential than considering the lock-in range of the PLL. Hope you understand.
Yes, sir. Okay, sir. Thank you.
Yeah,
Sir.
yeah.
Any other participant? Don't hesitate, because if you are having even a very small question, you feel that it's
Yes. You can ask me.
Yeah, you should ask, because for beginners it becomes really a problem. Sometimes they even do not understand the basic principle of many things. So if you are having any doubt, you
right.
ask. Because there are many students who are beginners in the research field. So maybe they are not aware of the PLL. Actually, PLL in you can say simulation, and when we are going to use it in hardware, it may not behave similar what you have studied. So that is very important if you are having experience of such PLL. And Dr. Chitti Babu is having the experience, so I hope that the students should take the advantage that he is here, and they can ask the questions. So any participant, if still he or she is having any question, please ask. Okay, I'll have one small doubt.
Yes.
How much delay a PLL usually introduces in the system in the real-time application? Have you encountered sometimes that because of PLL, the actuation becomes a difficult task, or it is being delayed sometime?
Yeah, you are rightly asked this question, Professor. Actually, we encountered while we are implementing the control on the inverter, because this case study we have done in the hardware in loop, and we never experienced the difficulty in real time. But while we have implemented this AGTFT PLL for implementing the control loop on the voltage source inverter, Professor, that we have done. In that work while implementing, right, first of all, the difficulty encountered is that while we are generating the PWM pulses from the driver circuit, that the PWM pulses is corresponding to the switches of particular phase. So that phase sequence as well as the inverter output voltage phase sequence, both must be same. You know, while we generated the PWM PLL, I mean PWM pulses for that inverter, initially the phase sequence of the PWM pulses are not in the same as that of the inverter output voltages. Say in the PWM pulses corresponding to ACB, for example, inverter output voltages phase sequence are ABC, then it causes the problem. There is a kind of overcurrent in the DC link voltage. We experience a difficulty. Then we thought of, and moreover, you cannot give a direct DC link voltage at a high voltage level. During such situation, it caused the more circulating current because of high DC link voltage. So that is what we made the study with a reduced downscaled laboratory, that we have taken 60 volt AC line to line as inverter output voltage. Then we took DC link voltage of 120 volt. Really, it is a very challenging task, Professor, while implementing the control, especially on the phase locked loop. again the synchronizing the inverter output voltage and the PWM pulses of the driver circuit itself is a challenging task that we encountered, and we have solved that issue. So the second is what the problem we faced is that as we have implemented the control in the D space DS1104, that DS1104 itself having the limited sampling frequency range.
Yes,
But
yes.
when you are operating the inverter at a very high switching frequency, and again the problem associated with generating the PWM pulses, professor. That is what we have done the inverter with a switching frequency of 2 kHz corresponding to DS1104 and the clock frequency. That also we face a difficulty, professor. Of course, while implementing the PLL in the control strategy, generating the PWM pulses to implement, it's a very challenging task. We face the difficulty. Of course, so doing the simulation is completely different from the real-time validation, what the problem we faces. Of course,
Yes.
and also many problem, professor. Not only that, even from the driver circuit also the PWM pulses are not generated very properly. We found every time there is a over voltage indicator on the DC link, and we encountered one by one problem. Then finally, almost the scholar took 3 years to understand to make the complete experimental setup in the laboratory. Now we could implement the entire control algorithm, whatever we are developing now.
Yes.
Yeah, you rightly said the simulation platform, whatever we realize and we see the result, the same results we never expect from the hardware. It has a number of reasons, and that is what someone should work very dedicatively and understanding the hardware as well as having the fundamental knowledge and the implementation. Then we could be able to implement in a real time. We can validate both simulation as well as hardware.
Yeah.
Yeah.
Thank you very much. Actually, I just wanted this to be discussed with the participant because many of the participants may be having a doubt that this is a very simple PLR, and if we get a result, we can get a publication in IEEE transaction. So to have a feel that if you want to publish in IEEE transaction, definitely you have to pass through those challenges which you will feel in the real-time implementation. So those things are very much important. Thank you very much. You have nicely explained this, and it is really a problem to have a PLL in real-time application.
Yes, professor. Yes, thank you very much, professor. It's all with your our professor Beam Singh only. We could read a number of research paper. We could completely find the entire research paper. We used to follow that. Even professor, I think you both are from the product of Professor Beam Singh, so we used to follow the entire research work, and we could gain our knowledge in this particular area, professor, because he has done an extensive research in the control and implementation of all grid solar PV system for both grid connected as well as standalone. Okay,
yes, yes.
That is what the key motivation for us to follow his path. That is what. Yeah.
Really nice. Thank you very much that you had accepted our invitation to be the part of this faculty development program. And we hope that we'll continue this. We would be inviting you sometimes in a physical mode, so that at least you should visit our institute and see our labs also.
Okay. Sure, sir. Thank you very much. It was my pleasure to be a part of that. Dear participants, you can note down my email ID. If you need any help or anything else, please let me know. So definitely I will revert back to your email. And thank you all. And thank you both for inviting me for such a very wonderful FDP during this wonderful evening time. And thank you, Professor. And namaskar.
Thank you very much. Namaskar. On the behalf of our institute, MANIT Bhopal, I extend my sincere thanks to Dr. Chitti Babu for delivering such a nice lecture and discussing the PLL. Hope the students might have got the benefit, and we would be discussing these things in those physical mode in the next week, where we will be going to discuss it in laboratory. So basically we can say that we have a theory part, and we will be going for the practical part in the next week.
Okay.
So thank you very much once again. Thanks, sir.
Thank you, sir. Thank you, sir. Shall I make a leave, sir?
Yeah, sure, please.
Okay. Thank you, sir. Thank you all. Yeah, thank you, sir.
Now to all the participants, just now I think Dr. Shailendra has mailed you 2 papers. Yesterday I had discussed about the papers that we would be having 2 research papers related to energy storage technologies. So Dr. Shailendra will be discussing about those 2 papers, and it is in your mailbox. So you can just go through that paper and try to find out the, you can say, takeaway from that paper, what you understand from your side, because it is really important for the beginners in the research or in means PhD or PG, that if you are reading a paper, how you should understand. Usually we say that reading between the lines. That means whatever is written in the paper, sometimes it does not appear to be very simple, or sometimes it appears to be very simple, but it is not very much easily implementable. So both the things are very much important, and that's what we wanted to have through these 2 papers, the orientation of our faculty development program, that if there is any paper, how you should proceed to see the paper and what are, I can say, important takeaways from that paper, how to identify that. So usually what we say that this paper is very simple, how it has got published in IEEE transaction. But if it is published in IEEE transaction, you might be overlooking some of the very important features of that paper, looking it as a very easy one. So Dr. Shailendra, are you able to discuss? Please turn on your unmute your mic. Dr.
Hello.
Yeah, okay. So
Yeah.
it
Is it audible, sir?
yes, it is audible. So you please discuss those 2 papers, brief about the papers, and we will just ask all the participants to go through the papers, and Dr. Sel, what you can do, you can just pose few of the questions, so that at least they should start with those questions, like it's a reading comprehension and getting the answer to the question. So you can ask few questions, that what is in that paper, brief idea, and let others read, and then we will discuss in coming sessions. Okay.
Sure, sir. Sure.
Yes.
What we can do, sir, after this particular session, I'll mail the questions to them so that they can identify, and they can, I mean, it can be discussed in next, whenever we will find time, then we can discuss these questions and queries, as well as the solution for that particular question at next session. I mean, tomorrow, today I'll give the questions, and tomorrow we shall discuss these questions. We can also ask the participants that what would be the solution for that questions. So can someone share these papers? Can someone share their screen, those who have got these papers? So I have mailed 2 papers to you. One is based on, if you can check your mail, one is based on simple energy storage for microgrids. Okay, for microgrids, for we are having this large storage as a grid, and then other side we are having PV array simple, and then we are having this battery energy storage. So 3 basic components are there. Okay, and so the title of first paper which I have shared, that is this norm proportionate based approach with mod transition between grid interactive and standalone of solar battery energy storage.
Shailendra, sharing. Just wait, I am sharing.
Okay. 3-phase 4-wire microgrid. Okay, so here, I mean, simultaneously, I'll tell you what are the basic components which are required to publish a good paper. Okay, because sometimes you will find out you are having a good experimental results, you are having good diagrams, but still you are not able to publish. So what are the things which are required to publish a good paper? Okay, because most of the, I mean, here are researcher, or we can say PhD scholar, as well as MTech scholars, those who are looking for publication in good journal papers, in good journals. Okay, so here if you see, like in first paper, we have given this mod transition approach, first one, and along with we have put the battery energy storage. So can you think what would be the role of battery energy storage in this particular paper? If all are requested, please open first paper in your laptop, mobile, whatever you are having with you. Please open the first paper.
Can I share, sir, paper?
Yes.
Yeah.
Okay.
So if all are there, can you see that what is the basic thing, why we require energy storage in this system? Can you think? As we have big storage grid in this system, so what is the need of a small storage? As grid can infinite infinite amount of energy, as well as it can give or it can supply infinite amount of energy. So what is the, if grid is there, so what is the need of this battery energy storage? Can you think, or can you tell me, anyone? What is the requirement of this battery energy storage here? Because as we are having these grid connected solar inverters, okay, so grid is the biggest storage in solar inverters. As today Chitti Babu has discussed a lot of things related to grid storage, like how we can store the energy in grid, or how we can fed the energy, how we can synchronize these PV array or solar system with the grid. So what would be the basic thing, or why we require energy storage in it? In microgrid, why we require energy storage? Anyone?
Sir, because source is intermittent in nature.
But in grid connected converter, we don't have any kind of storage. So PV array is there, and PV is intermittent in nature. So how we handle in grid connected converters? Yeah, I agree with you.
So maybe
but how we handle? Yeah.
So maybe fault during islanded mode, we require this kind of system.
During islanded mode, we require this kind of system. Yes, exactly. So energy storage is, if we talk about earlier, whenever the cost from the energy, the cost of energy from the PV array was a little bit costlier. Okay. So, if we are talking about the scenario before 2050, so PV energy was a little bit costly as compared to the grid energy, okay, or the power which we are drawing from the grid. But as people are adopting this solar energy, people are installing these solar energy at their roof top, as well as on the big buildings. So the cost of this PV energy is goes down, and as the PV energy goes down, so people are adopting it and they are putting along with the grid. So the burden on the grid, if you see the peak hours, the burden on the grid has been reduced. Okay, so load demand can be fulfilled by these renewable energy as well as from the grid. So solely the burden on this load demand, or we can say burden on the grid, has been reduced. But what will happen? So at that moment, in grid connected mode, we don't require battery, as we have fulfilled the load demand. So if you are having, suppose I'm having a 5 kilowatt solar in my rooftop, and during daytime, I'm generating the energy, I have fed the energy to the grid, and night time, when the PV is not there, I can draw the energy from the from the grid in night time, as well as in daytime. I can fed the energy to the grid as well as to the load. I mean, if 5 kilowatt I'm generating, so if load is my load is 2 kilowatt, rest 3 kilowatt I can send to the grid, and in night time I can draw energy from the grid. So there is no requirement of energy storage. Any kind of battery we don't require in grid connected converters. Okay. So this system is very valuable where the grid is there. Where? So what is the main disadvantage of grid connected converters? We require grid all the time. We cannot say like grid is there and grid is not there for some times, because this synchronization unit, as discussed today, without grid, without these grid components like voltage, frequency, as well as voltage angle, we cannot synchronize our converter with the grid. Otherwise, if converter output voltage is not matching with the grid voltage, one large circulating current will flow through the load as well as converter and grid. So there is requirement that we have to maintain certain voltage, certain frequency, and certain angle. Like IEEE 1547 says, like you have to maintain the magnitude within plus minus 10%. Frequency you have to maintain like 0.2 or 0.3 hertz, depending on the system rating, as well as angle, the difference between converter output angle, voltage angle, as well as grid voltage angle, it must be less than 2%. Then only we can synchronize our converter with the utility grid. Okay. So this way we have identified like what is the basic research. Okay. So people are inventing, people are already implementing these solar connected inverters. Already lots of renewable companies are there. They are implementing these renewable energy converters. So if you go to the normal renewable energy converters, suppose I'm having a grid solar and in between I'm connecting one voltage source inverter. This is the simple converters or simple grid connected converters. So what is the utility of this converter, or what is the utility of this system? So we have to identify what is the exact issue in the existing system. If you are having a grid connected converter, so we have to see what is the issue with the existing system, how we can improve or how we can address that issue in this particular paper. So what we have to do, we have to do the literature review. That's why we are starting our research, or people are saying whenever you are going to, or any researcher, any faculty, any PhD student, the basic thing is find out the research gap. What is given, what is already existing, and what is the advantage, or what would be the research gap by developing new system. What would be the advanced system which you are going to develop, any control algorithm, any system configuration, updated system configuration which you have developed, any dynamic response you have improved. So every time a reviewer will ask, what is the novelty in your system? So you have to highlight these points. Okay, you have to highlight these novelty in your system. So suppose I'm having a normal grid connected converter, Nowadays, you will see that lots of people are working on power quality. They are saying like grid connected converter is there, but it can work in daytime as a grid connected converter, or we can say solar inverter. But night time, when solar is not there, it can operate as a D-STATCOM or power quality conditioner unit. So if daytime you are utilizing this power converter as a solar inverter, nighttime you can utilize as a D-STATCOM. The utilization factor of that converter is improved. In daytime, what will happen? Daytime you are utilizing, nighttime you have to shut down because solar energy is not there, so active power flow will not be there. As in all the inverters, if you find out, we are having 40% spare capacity in every voltage source converter or in every converters. So what do you mean by 40% spare capacity? 60% we can share the active power, rest 40% can be utilized for harmonic elimination, for other purposes like load unbalancing, harmonic elimination, reactive power compensation. Okay, unity power factor operation. So 40% capacity is not utilized when we are having only grid connected converters. Okay, so how we can utilize this 40% capacity of the inverter so that the utilization factor of the system can be utilized, increased. Okay, so what here we have done, as you can see the in system configuration, we are having one VSC, and this VSC is connected with the PV array as well as this battery storage, and then we have connected with the AC grid. Okay, so the second part, we have improved this converter from grid connected converter only as a power quality conditioner also in night time. But still, what is the issue with the system which you have reached to second stage, like solar plus power quality improvement there, solar integration plus power quality improvement is there. In third stage, when the again you have to identify what is the issue with the second system. What is the issue with the second system? Can you identify what is the issue? As I told you in first part, you are utilizing this system as a power quality conditioner, but you need to stop your inverter. You need to shut down your inverter when grid is not there. In rural areas like city, I mean urban cities like Bhopal or some in the, some part of India like Delhi, Bangalore, you will identify grid is there. But if you go to the rural area, still we are finding out like there is outage of grid. Means the time period has been reduced from earlier we were find out like grid gone for 10 hours, but now we are having less time, like we are the grid is not there for 3 to 4 hours out of 24 hours. So during this 3 to 4 hours, how we can utilize these powers, or how we can power our equipment using our microgrids. So in this moment, you require energy storage. You require this energy storage. So in this way, we can connect our battery energy storage here. So people are saying like you are including the costly component, but if you want to power your load for these 3 to 4 hours, it is the mandatory component. It is the mandatory component. Or nighttime, like nighttime PV is not there, grid is not there. So how you will power your 3-phase load? We require this time battery energy storage. So this is the importance of this battery energy storage along with it. So you can see the key point, how we have to address the problem by selecting first system and reaching to third system. Okay, so you have to go step by step in your research. Okay, you have to identify your what are the issue with that Dixon system, and then you can go. So here what you will find out in this particular system or in this particular literature which has been published in IIITDM Transactional Industry Application, we have given in introduction abstract. You can go through it in introduction. At the last of introduction, can you scroll up? Yes, can you go to the end of introduction? Here, yeah, right side, you can see that I have given novelty in points. Okay, I have given 7 points. What are the main features of this particular literatures? How it will help, or what is the novelty in this system? So these points you have to include in your papers whenever you are going to write, because nobody, if you if you tell you about the reviewer, they used to do this. Some of the people, they are going for a critical review, but most of the time you will find out nobody is having time. Okay, right now, nowadays. So what people are doing, in half an hour or in 15 minutes, they are completing the review. So nobody will be interested to read out your whole research. Okay, whole introduction, then system configuration, then control algorithm, what are the result and discussion. They will scroll down your paper. First they will study your abstract, and then they will go to the key points. So if you have given the key points, they will directly read these key points, that these are the key points which has been covered by authors, and then they will judge your paper. But if you don't have key points, they are not able to judge, and they directly reject your paper. So it is mandatory. You can see, if you want to publish in a good journal, it is mandatory to give some basic points or some basic thing along with this particular paper. And here, as we are having this particular system configuration, you will identify like solar is connected with the boost converter, and other side, this storage, battery energy storage, is connected with the bidirectional converter. Okay. So here it can be controlled, like how we can have this battery energy storage, and how, when this battery energy storage will supply the power, and when the battery energy storage will be charged. So here there's this disadvantage, as I told you, this energy storage will be discharged only because it is a costlier component, and the life of the battery may deteriorate when the charging and discharging cycles are more. You will, after 1 hour you will charge the battery, after 1 hour you will discharge the battery, and number of charging and discharging cycles are more. You are deteriorating the life of the battery. So the first target will be, if you are having PV array and SOC of the battery is less, state of charge of the battery is less, the priority is to charge the battery. And after that, if you are having any excess power, then we can feed this power to the grid. If this PV array is not there and battery energy storage less, SOC is not into the remark or as per the limit, we can charge this battery through the grid. So you can see that this is not a simple VSI, voltage source inverter. This is a voltage source converter. So what is the difference between VSI and VSC? It can also work as a rectifier. Okay, it can work as an inverter, but this is a bidirectional converter. It can we can take power at the DC bus from the AC source, as well as we can convert this DC power into AC. Okay, so at that particular moment, we can charge this battery from the grid when PV array is not there. We will discharge the battery only when both the main sources are absent. Like PV array is not there as well as grid is not there, so we'll discharge this battery. Okay, so this is the basic idea, because we have to have this, we have to keep these charging and discharging cycle low or minimum, so that we, because here if we talk about microgrid, nobody will put costly lithium ion battery, as energy density of this lithium ion is more as compared to this lead acid battery. Okay, so people are seeking, like in microgrid we can put this lead acid battery, as it is not much costlier as compared to lead acid battery as compared to lithium ion. We can put here lead acid battery, but energy density of this lead acid battery is less as compared to lithium ion. So lithium ion having a good energy density, and people are using in electric vehicles. Okay, so this way we can have this this system. I would request everyone, please go through this particular paper. Here we are having control algorithm, then few results. We are having what is the control structure, because control is playing important role when we are going to have this inverter. We are having standalone as well as grid connected, and how the mode transition will be decided. Depending on this, we can operate our system in grid connected as well as in standalone mode. We have also discussed the control of energy storage in this particular paper, so you can go through it. And I'll give you few questions. I have given the overview of this particular paper, what is given and what is the main features or main target of this particular paper. And I mean, if you are having a new control, you can also publish. If you are having new control, you can control in better way. You are most welcome. You can get one more IIITDM transaction if you are having good these results. So with this, I'm going to conclude it. And yes.
Sumit Kataria has asked some question. Yeah.
Sir, sorry to interrupt you, sir. What is the meaning of LP nor proportionate base?
So this is the adaptive control. And here this LP norm, based on normalization, we are normalizing the control. We are having some metrics for this control, and using this matrix we are implementing this control. So norm means we are having some kind of matrix over there. This matrix is implemented in the form of equations. You can see it in control. If you go to the control, okay, can you scroll down?
Rajinder, scroll down.
Yes, can you go to the control block diagram? So here you can see that we have given some norms as well as some factors are there. Signum function we have utilized, as well as some this GM we have utilized. So you will find out lots of components are there which are involved, and they are making this control. So whenever you will implement this control, you will find out like how we can. So this is the kind of adaptive control, nothing else.
Okay.
Okay.
Thank you, sir.
Yeah. So this way we are having this control, and we are using for VSC control. Yeah. Any other questions?
Thank you, sir.
Okay, so we can conclude today's session, and we'll meet tomorrow. Tomorrow, Dr. S.K. Singh from IIT BHU will be discussing, and it will be on the fast battery charger, I think. Shailen, is it on fast battery charger?
Yes, sir, it is based on SiC based devices for battery energy storage application.
Okay.
So he will discuss some SiC based fast switching devices as compared to normal IGBT, how we can make the converters. and used for energy storage applications.
Okay. All the participants, please join the WhatsApp group, and there we'll be sharing. Initially, we have shared the schedule for this week, so that schedule will be followed throughout this week, and for next week we'll be discussing and we'll be finalizing that schedule, because like you participants, there are some of the professors also who are not getting ways to reach Bhopal, so maybe there are certain hiccups in reaching at this stage. So we'll just let you know about the status, and please go through the details. Again, I will say that please go through the details, because your evaluation will be there. Usually that is to be cleared by all the participants, so probably you all will clear, but you must be aware of those things, that on what basis your evaluation will be done. So please go through the link of ATAL FDP scheme document, and there you can see all the documents. Okay, so we close for today. So take care, good night, and we'll meet tomorrow.
Okay, sir. Thank you.